Everybody, welcome to Video Notes 3.1, where we talk about covalent properties and naming covalent substances. So make sure you can do these 5 bullet points when we're done. So read sections 12.1 through 12.4 and do the self-check 12.1, and it's on page 345. Put it in your notes. So why do atoms bond? Okay, so bonds are what holds things together. Why do atoms make bonds? Well, we think it's because they're more stable. And we think it's because they're more stable when they're bonded and their valence shell is full. So here's fluorine with 7 electrons in its outer shell. So if it bonds with another fluorine atom and they share those 2 electrons right there, and that means that this fluorine has 8 around it and that fluorine has 8 around it, and it's more stable. Okay. Same thing with hydrogen and chlorine. So here's hydrogen with its 1 outer electron. Here's chlorine with its 7 outer electrons. If they overlap their orbitals and share those 2 electrons that were single, then chlorine has 8 around it and hydrogen has 2, which makes hydrogen stable because it's so small it only needs 2. Chlorine stable because then it'll have 8 in its outer shell. So that's how they bond by sharing electrons. How do atoms bond by transferring electrons? Well, here's sodium with 1 outer electron. Here's chlorine with 7 outer electrons. If chlorine's electron is transferred to if sodium's electron is transferred to chlorine, then sodium becomes a +1 charged ion, and its used to be inner shell is full. And chlorine's outer shell is full if it has a -1 charge, and this is the bond, and it's called an ionic bond. So, what property of atoms allows them to share or transfer electrons? We came up with this property. I wasn't there, but scientists have come up with this property called electronegativity. And the higher the electronegativity, the more an atom can pull on another atom's electrons. So 2 atoms can share electrons equally if they both have about the same electronegativity, and they make what's called a covalent nonpolar bond. And so this purple cloud is the electron density being shared evenly. A covalent polar bond is this electron cloud, but this atom over here is pulling on the pair of shared electrons more than this atom. So this atom's kind of negative because that electron density is closer to its side of the bond, and this atom's kind of positive. That's electrons are equally shared for a nonpolar bond, unequally shared for a polar bond. But then an ionic bond is when the atom that has the stronger pull on electrons pulls the electron away from the atom that has a lower electronegativity, and you get positive and negative charged ions, and that is an ionic bond. So there's this continuum of bonding. It can be anywhere along this continuum, and so there's sharing characteristic and then ionic characteristic, and it all depends on the difference in electronegativity, but mostly it depends on the kind of atoms involved, okay? So END is electronegativity difference. So subtract the atoms' electronegativity, and you'll find out that in general, if electrons are shared equally, it's a nonpolar covalent bond, and there's no poles or differences created in their electronegativity, and they share the electrons evenly. If there's a medium difference, if you subtract and you get 0.5 to 1.9, it's called a polar covalent bond, and they share electrons. So here's what's happening to the electrons, share electrons. But the atom that has a higher electronegativity gets the shared pair closer to it, and so there's poles created, opposite sides. But then if there's a big difference in electronegativity, then the electrons get transferred from low electronegativity to high. Let's practice. Here's the cutoff line. In general, a metal and a nonmetal will make an ionic bond, and 2 nonmetals will make a covalent bond. But we can use electronegativity to help. Nitrogen is 3.0, oxygen is 3.5. What's the diff? It's 0.5. Now, it doesn't matter which one's bigger, it's just the absolute value difference. So 0.5 is a polar covalent bond. Polar, because it's one atom has more of a charge. Covalent, because they're sharing. And bond, because it's what's holding them together. F to F. So F is 4.0 and 4.0. What's the diff? It's 0. 0 means equal sharing of electrons, so that's a non-polar covalent bond. Let's find lead. Lead's right here, 1.8. Metal, fluoride, fluorine, well, fluoride. So the difference is 2.2. That's an ionic bond. And so that means fluorine is going to pull the electrons away from lead. Carbon is 2.5. Hydrogen is 2.1. What's the diff? 0.4. So they're going to share pretty equally, so it's non-polar covalent bond. All right, let's play. Look at this periodic table. All right, now what I want you to notice is that the red numbers are electronegativities. We have it on the periodic table we use, but I want you to notice what happens as atoms get more non-metallic. They become higher in electronegativity. So fluorine is a winner, chicken dinner. Francium's the biggest loser, okay? So you can see that metals tend to not pull on electrons, so they're going to give them away. Nonmetals tend to pull on electrons, so they're going to try to take them. But if they're bonding with another nonmetal, then they got to share. Okay. Covalent bonds. Co means together, yay. Valence is the valence electrons, so sharing valence electrons to make a bond. Oh, sharing, yay, we love to share, look at them sharing. Okay. So what kind of atoms are generally going to make covalent bonds? Nonmetals. Sometimes we call covalent bonds between nonmetals directional covalent bonds because the valence electrons that are being shared are stuck with the atoms sharing them and they can't flow around. So one of the rules to fill an octet rule, a guideline to help us decide how the atoms are going to share electrons is so that they can have 8, all right? When electrons are being shared, it counts for both. So this caret's being shared, so this, I think it's a gerbil. This gerbil gets some of the caret, that gerbil gets some of the caret. And so they're sharing, so it counts for both of them. So an example is NH3, nitrogen is going to share electrons with hydrogen. And I'll tell you what that means in a bit. Okay, so here's a shared pair of electrons. That means hydrogen's holding on to them and nitrogen. They're sharing. All right, so covalent bonds. Sharing electrons usually makes individual molecules. Okay, so here's H2. H sharing electron with another H. So then this is a molecule. All right, H2O. All right, oxygen sharing with hydrogen, oxygen sharing with hydrogen. So this is a molecule. So a lot of times these covalent bonds make molecules. Sharing electrons can make a network of nonmetal atoms sharing in a lot of directions, and that's called a covalent network solid. So like diamond. So here you have carbon, right? And carbon, and carbon, and carbon, and carbon, and it makes like this diamond form, right? And the sharing goes on and on and on, and it's sparkly. Okay, so that's a covalent bond in this network. So these aren't really molecules. It's just sharing in a lot of directions. There's also sharing like you learned when Mrs. Egan was in class. You have long chains, sharing, 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 and then they can cross-link and share, or if it's a different kind of cross-link, it'll be different. But you get these long chains of sharing electrons, and you can make polymers. So covalent bonds can make different kinds of substances. Right. So what would you see if there was covalent bonds present holding things together? Okay. So these are general. Notice I put in general. They don't conduct electricity because in order to conduct electricity, you need electrons to flow. But in these compounds, the electrons are being shared and they can't flow around throughout the whole substance. Variable melting and boiling point, some high, some low. But sharing and covalent bonding is the only type of bonding that allows for low melting and boiling points. Okay, so we're going to talk about ionic bonding and metallic bonding, and those aren't going to have low melting points, but covalent bonding could, but that doesn't happen. When they share electrons, they can make polar molecules or nonpolar molecules. Covalent polar molecules can dissolve in water, but a lot of molecules are insoluble. They won't dissolve in water. Okay. Covalent substances can be solid, liquids, or gases. There might be strong bonds between atoms, but then what's to make a molecule? All right, so this is a pretty strong bond between the H's, right? But what's going to hold this H2 to that H2? Not much there. So those are called intermolecular forces. This is strong, covalent bond strong, but these two aren't attracted to each other, so that's why hydrogen could be a gas. So variable states of matter depend on if it's a covalent network or a long covalent molecule, that kind of stuff. All right, so electron or configurations and orbital diagrams can help us predict what an atom's going to do. So here's oxygen's electron configuration. Here's another one. I flipped it over so you could see these two open orbitals, and those two and the other oxygen can overlap, right? And so then that would fill up, and that would fill up when they come together, right? And so then this oxygen and that oxygen could be happy if they're sharing two pairs of electrons. Woo-hoo, that's going to make a happy molecule. Hydrogen, okay, one here, one there. So if two hydrogens get together, then this hydrogen and that hydrogen, all right, there's H and there's H and they're sharing. Woohoo, let's make a molecule, yeah. Okay, and then I want you to try to figure out what element this could be representing and what might happen there, okay? So do it, think about it, we'll talk about it. So covalent molecules. So what a molecule is two or more atoms sharing electrons. Okay, that's what a molecule is. To make a little molecule. It could be a big molecule, could be little. So this is a molecule. This is a molecule. That's a molecule. Here is a line that represents shared electrons. So this molecule is sharing 2 electrons. This molecule is sharing 4. That molecule is sharing 6 electrons. And so those are different kinds of bonds. Okay. So molecules don't have to be the same atom. These just all happen to be diatomic elements. But what a molecule is 2 or more atoms sharing electrons to make an individual unit called a molecule. Okay. So what are we going to call them? Well, we got to call them something. So we're going to use prefixes to tell us how many atoms of each kind are in the molecule. Right? And you know it's going to be a molecular compound when you see nonmetals. Right? So you need to memorize these prefixes and what they mean. Mono means 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. It's a lot. So 1 through 10, counting, this means how many of an atom there are. The second word in these molecules, because it's going to be 2 nonmetals, there's going to be 2 words. 2 words. First word is going to have a prefix unless it's mono. Second word is always going to have a prefix and end in IDE. So let's see. Let CO be your guide. So CO is a molecule because it is compound, but it's made of a molecule, carbon and oxygen. So what we call it is carbon monoxide. So you're probably saying to yourself, what's going on? Well, there's no prefix in front of carbon because if it's mono on the first, you don't need to put mono. Every other time, the atom needs a prefix to tell you how many. And then it's not a double O here, so it's monoxide because there's 1 oxygen, and then the ending's ID. Let's practice. Okay? This is sulfur and fluorine. There's 1 sulfur and 6 fluorine, so we don't need mono on the first, so it's sulfur. And then fluorine, there are 6 of them. 6 was hexa, and then you have to change the ending to ID. Right? It's phosphorus. Do I need a mono? It's monophosphorus, but we don't need mono because it's the first one. That's the only time you don't need a prefix. And then 5 is penta. And then chlorine changes to chloride when it's the second group. Okay. This is H2O, 2 nonmetals. Nonmetals. So this is 2, so we need dihydrogen. And then 1 oxygen, and it's the second element, so we need dihydrogen monoxide. There's been a protest and a petition going around, so look up dihydrogen monoxide on the internet. Decanitrogen monoxide. Okay, so we got nitrogen, we got oxygen. How many nitrogen? 10. How many oxygen? 1. Okay, I totally made that molecule up, but at least you can figure out how to make it. Trinitrogen monosulfide. So we got how many S's? Just 1, so I'm good there. How many nitrogen? 3. Okay. Hexasulfur, S. Dichloride, chloride comes from chlorine. Hexasulfur, 6 sulfur, 3 chlorine. All right, I made these up. I don't even know if they exist, but I just wanted to practice the prefixes and show you. Okay. All right, diatomic elements. So we know di means 2 atoms. Right? Now you can have diatomic compounds, and the atoms have to be different, but if it's an element, the atoms have to be the same. So there's 7 of them that naturally exists. This is how you find these elements in nature. So you never walk up to hydrogen and there's going to be 1 of them. Every time you walk up to hydrogen in nature, it means an element, it's going to be 2 of them. So these diatomic elements, memorize them. But I have a way to help you memorize them. Get a periodic table, find element number 7, which happens to be nitrogen, And look, it makes the number 7 on the periodic table, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's only 6. Don't forget about hydrogen over there. Okay, so as long as you have a periodic table, you can find the 7 elements that exist as diatomics, and you can memorize them. There's a word for it too. All right, North. So North. You gotta phlegm up the H, like it's an accent or something, so you don't forget it. So whenever you see these elements as their natural state, they're gonna be diatomic. Right? You're probably used to oxygen being diatomic. All right. So that's what we're talking about for covalent. We have a lot more to do, but that's all for these notes. Make sure you read this section, and then you gotta love ChemCat, right? So anyway, make sure to ask questions, write down stuff, draw pictures, and these are the things you're supposed to be learning for the first objective. All right, peace out.